Goodbye. This is Larry. This is June 27th, day 27th of the June Leetcode Daily Challenge. Hit the like button, hit the subscribe button, and let's get started. And join the Discord and hang out and share and whatever. Perfect square. Given a positive integer n, find the least number of perfect squares. For example, 14916, which sums to n. Okay. What is the number n though? So for small n's, you can definitely do dynamic programming. The question is, when can you be greedy, right? Can you be greedy with this problem? Well, clearly not so much, because for 12, if you do greedy, it'll be 9 plus 1 plus 1 plus 1 plus 1, or 4 plus 1, and that'll be 5 numbers, right? So for example, 12 is equal to 9 plus 1 plus 1. Oh, that's 4 numbers, I can't count. But shorter would be what's given in the example, right? So greedy in this case wouldn't work. The question is, because they don't tell you the n, which is a little bit unfortunate, can you use dynamic programming, or you have to do some kind of crazier math? So I think for now, I'm going to try dynamic programming. We'll see if the time runs, but it's because we don't know the constraint of the problem. And yeah, and with dynamic programming, it's very similar to coin change, which is what. But the problem that you should ask yourself exactly in a recursive kind of way is, well, if I have this number n, what is the fewest number of perfect squares that sums to this number? And then you ask that recursively by saying, okay, if I subtract one perfect square, what is that number going to look like? So that's basically the problem, and then we're gonna let's solve it. Let's see if it's good. I don't know the n, so it may not be good, because if you have if n is, for example, 1 billion, well, then it's not going to run, because dynamic programming trades space for some of that time, and you can't have 1 billion space, at least not right now, maybe in the future. So yeah, let's kind of figure that out. So I'm going to write the cache portion first. Let's just write the recursive part first, which is def of min s for short of some n. And now we just have to do, okay, so let's just say the current is equal to 1, and then while current times current is less than or equal to n, our best answer is equal to infinity, because we haven't done anything yet. Or actually, our best answer is at most going to be n, and the reason is because, if you just take 1, which is a perfect square, n times, that sums to n. So that always will be the case. And then now we take the minimum path, where it's n minus current times current plus 1. Oh, sorry. Equal min s plus 1. So it's whatever. So this means that we add 1 to the number of perfect squares in our search, and this means that we subtract one of the perfect square, which is current times current. And then we now take the minimum path, going almost like the shortest path of this path to the current best that we know, and at the very end we return best. And that's pretty, oh well, and then you increment current, because you should increment stuff, otherwise it would just be an infinite loop. So that's kind of the way you would solve this problem. And now we have to figure out how to cache this, because this would go infinite, right? So let's, for example, I don't know if 12 even runs, but we could definitely try for a big enough number, and it won't run, right? Oh well, it would run a little easier if you call the function first. So yeah, so this is correct, but for a bigger number, let's just say maybe even 10,000, it shouldn't work. So yeah, so now you're getting to see time limit exceeded, because this is exponential in that for every bigger number it branches out multiple times. And yeah, and now so you're trying to focus on the caching, so we can let's create a cache. of, let's just say, -1 times n plus 1. And we choose this number n plus 1 because there are n plus 1 possible inputs, because for this input n, maybe I should have used a different variable, but n goes from 0 to n, and here there's n plus 1 distinct numbers. So those are all the possible inputs to this number. Yeah, and also we could actually, now that I look at it, you could start current at 2 because n minus 1 will always just be this answer at the very base case, so you don't have to test for it. Actually, is that true? Actually, I don't know if that's true. Let's just keep it this way. And then we just have to do if it's calculated, right? So is calculated is equal to force times also n plus 1. So now our caching will be if with this input we already calculated, then we return it from the cache. And that's it. And at the very end, we put things back in the cache. Is equal to best is calculated is equal to true. And now we can run it again and see if it runs fast enough. Yeah, so much faster, though still a little bit slow. I don't know what the n is again, the constraints of the input. Usually they tell you, but I think for all the problems they just don't. Well, that's a little bit slow. Oof. So that's a little bit unfortunate that even for 100,000, that's a little bit slow. We can make... Yeah, I mean, I think this is okay. Okay, so apparently for 100,000 is just maybe too slow. I don't know what the bounds of this input is, so I'm going to just submit it. In an interview, I would just talk about it with the interviewer. Now, because I'm doing it myself, I can only submit to see, just to see what the bounds of the input is. It may be that it gets time limited, and I'm okay with that because I don't know. They don't tell you. Yeah, there's no communication here, right? And it turns out that it is accepted, so maybe that is the expected behavior. So you may ask yourself, what is the complexity of this algorithm, right? So the complexity should be roughly n times square root of n. And the reason is because for each input, well, there are n possible inputs, right? For each input, this thing happens about square root of n times, because they're because there's square root of n numbers before the current current times current is bigger than n. So because each input to this function does square root of n work, this is roughly and there's O of n and there's O of n input. This is roughly n times square root of n time complexity. And the space complexity is O of n because you can kind of see we only allocate O of one space for each input, so it'll be O of n space. You can maybe get a tighter analysis of this bound by noticing that on the smaller ends you don't go the whole n, but I might have to think about how that geometric sequence works, but this is approximate and good enough for me. Yeah, so that's all I have for this problem. This is you could say this is similar to other dynamic program problems like coin change and stuff like that. So it is relatively straightforward. On a tougher problem, it might require greedy if the constraints are slightly different. So yeah, that's all I have for this problem. Let me know what you think. Hit the like button, hit the subscribe button, and I'll chat with y'all later. Bye bye. After I hit the button. Okay.